Welcome, everyone. Today, we continue our journey into localization and mapping, the essential capabilities that allow autonomous robots to understand where they are and how to move safely in the environment. Up to this point, we have learned how scan matching works and why it is such a fundamental building block for map-based navigation. Scan matching helped us understand how a robot can align its sensor readings with a known map and reduce uncertainty about its motion. Now let's take the next step. Let's assume that you already have a map of the environment. Given this map, our new goal is to estimate the robot's position as it moves. This is a central problem in robotics because even small errors accumulate over time, and without proper localization, the robot quickly becomes lost. In this lecture, we introduce particle filters. We will first understand particle filters in general, and then explore how they are used in Monte Carlo localization, one of the most popular and powerful methods for robot localization in a known map. By the end of this session, you should understand what particles represent, how they evolve over time, how sensor updates refine them, and why resampling is crucial for maintaining a good estimate of the robot's pose. Let's get started. Now let me walk you through the lesson plan for today's lecture. We will move from intuition to analysis, gradually building a full understanding of how particle filter-based localization works. First, we begin with map making using HectorSlam. This helps us understand how a lightweight LiDAR-based system can generate high-resolution maps without needing wheeled odometry. It also gives us the map on which localization will operate. Second, we introduce particle filter localization. Here, we will build intuition about what particles represent, how they approximate probability distributions, and why they can handle nonlinear and non-Gaussian systems. Third, we study adaptive Monte Carlo localization, also known as AMCL. This is the widely used ROS package that dynamically adjusts the number of particles depending on the robot's uncertainty. We will look at how AMCL improves both accuracy and efficiency in real robots. Fourth, we connect everything to recursive Bayes filtering, the mathematical foundation behind AMCL. We examine how prediction and correction steps interact and how belief distributions evolve over time. Finally, we discuss tuning particle filters in ROS. We explore which parameters matter, how to adjust them in real-world environments, and how tuning affects localization stability and convergence. By the end of this lecture, you will understand not only how particle filters work in theory, but also how they are practically implemented and tuned in ROS. Let us begin by looking at a simple example. Imagine that we are driving a small autonomous car inside a university building, moving through long corridors and intersections. The car starts at the initial position shown in the image, and the green line represents the desired path that we want the robot to follow. In this situation, basic path planning only gives us very high-level instructions. For example, it may simply say, take the second right, then the second right again, then first right, first left, and finally first right. Although these instructions may be correct, they do not describe an actual trajectory or the exact geometric path. Instead, they only tell the robot which turn to take at each intersection. This kind of high-level path assignment works for simple navigation tasks, but it lacks the detailed motion information that is needed when the robot must move smoothly, quickly, or accurately in a real environment. And this limitation becomes even more critical once we transition from basic navigation to racing scenarios. As we begin to think about competitive racing, the limitations of basic path planning become much more obvious. In racing, it is not enough to simply follow a sequence of left and right turns. Instead, the car must follow race lines, the most efficient path through a corner that allows the highest possible speed. In the illustration on this slide, you can see a typical corner. The racing line is determined not only by the turn itself, but also by what happens just before and just after the turn. For example, a late apex, followed by early acceleration, can allow the car to exit the corner with a higher speed. This means the car must be aware of more than just the immediate turn visible in front of it. Good decision-making requires looking ahead. To choose the optimal line, the robot needs knowledge about the parts of the track that are still upcoming, so it can manage its speed, braking, turn-in point, and throttle transitions appropriately. In other words, choosing the best racing line is fundamentally a future-aware problem. On this slide, we see a more concrete example of why future information matters so much. In the diagram, there are two possible paths through an S-shaped corner. Both the red line and the green line follow an optimal path through the first turn. However, only the green line positions the car correctly for the second turn. The red line takes a line that looks good at the beginning, but it results in a poor position for the next corner, requiring slower speeds and delayed acceleration. In contrast, the green line sacrifices a bit of optimality in the first corner in order to gain a much better line through the second corner, ultimately allowing higher speed overall. This example illustrates that path selection must consider what lies ahead, not just what is immediately visible. Future-aware planning is especially important on racetracks where the sequence of corners determines the overall lap time. Formula One drivers know every corner before the race starts. In the same way, autonomous racing cars need global track information to make the best decisions. Over the next few lectures, we will explore the full pipeline that enables an autonomous race car to understand its environment and navigate through it. This diagram shows the high-level system overview. We begin with mapping. In this stage, the car builds a representation of the racetrack or the environment around it. Next comes localization, where the car estimates its precise position within the map it has created. Once we know where the car is, we move to path planning, where the system decides the best route or trajectory to follow. Finally, the control module takes the planned path and converts it into steering, throttle, and braking commands that the car can execute. This flow, mapping, localization, path planning, and control, forms the backbone of almost every autonomous robot system. And throughout this course, we will learn how each of these components works and how they fit together. To start this journey, we will focus on the very first component, mapping. In this course, we will use HectorSlam, a fast and lightweight SLAM algorithm that works exceptionally well with LiDAR data and does not require wheel odometry. HectorSlam allows us to build highly detailed, two-dimensional maps of the environment. These maps will serve as the foundation for localization and path planning later on. By understanding how the map is generated, you will better appreciate how localization algorithms rely on this information to determine the robot's position. To begin our discussion, let's talk about the concept of simultaneous localization and mapping, commonly known as SLAM. SLAM addresses one of the most fundamental challenges in robotics. It is often described as a classic chicken and egg problem. On one hand, you need a map of the environment in order to determine where the robot is located. But on the other hand, you need to know the robot's location before you can accurately construct the map. SLAM solves this circular dependency by estimating both the map and the robot's position at the same time. This is why SLAM is such a powerful and widely used approach in autonomous robotics. This slide illustrates the step-by-step process that SLAM follows during operation. The procedure begins with the very first laser scan. That initial scan, together with the known starting pose of the robot, is registered as the initial map. After this, the robot moves slightly during a small time interval. At the next moment, a new laser scan becomes available along with an estimate of how much the robot has moved. SLAM then compares this new scan with the portion of the map that has already been built. By finding how well the new scan aligns with the existing map, SLAM can infer how the robot's position has changed. Once this new pose estimate is obtained, the algorithm updates the map with the newly observed data. This cycle, scan, align, estimate pose, and update the map, repeats continuously. As time progresses, both the map and the robot's trajectory become more refined with each new measurement. Now, let's take a look at how the map actually appears as the car drives. At first glance, the output seems quite simple. Just a clean two-dimensional representation of walls and obstacles. But behind this seemingly simple result, there is a lot happening at the algorithmic level. To understand it more clearly, we will dive deeper and analyze the process from an implementation perspective. There are many different SLAM approaches in the literature, each with its own trade-offs, and researchers have compared them extensively. For our platform, we will focus on the method implemented in the ROS package Hector SLAM. This is the tool you will use to generate maps on your own vehicle, and we will break down how it operates and why it works well for lightweight, high-speed robotic systems. The map we generate is an occupancy grid. This is simply a grid laid over the environment, where each cell represents the likelihood of that area being occupied or free. In the image on the left, you can see how the real world is discretized into these small, square cells. Cells that consistently receive LiDAR hits over time are marked as occupied, and they form the walls or obstacles in the final map. Cells that lie along the laser beams but do not block the scan are considered free because the ray has passed through them without encountering anything. Any cell that has never been observed remains unexplored. Once this grid is created, every new LiDAR measurement must be translated into updates on specific grid cells. For that, we maintain a structured map where each cell stores information derived from repeated sensor readings. To express the LiDAR data inside the grid, we encode the measurement as follows. A value of 1 indicates the endpoint of a laser ray, meaning a hit, and a value of 0 corresponds to the cells between the robot and the hit, which represent free space. This simple binary representation helps us convert each scan into meaningful updates on the occupancy grid. Based on repeated measurements, each grid cell receives a state value. We assign 1 for occupied cells, -1 for free cells, and 0 for unexplored regions. These values provide a compact representation of what we believe about each spot in the environment. As new scans arrive, the cell states are continuously updated, refining the boundaries of obstacles and free space. To handle uncertainty, we define a measurement model. This model expresses the probability that a cell is occupied or free, given whether the LiDAR measurement indicates a hit or no hit. Although LiDAR is generally accurate, we cannot assume perfection. People walking through the scene or temporary obstacles may introduce noise. One challenge is that multiplying many small probabilities can quickly lead to numerical underflow. To avoid this, occupancy grid mapping works in log odds form. Using log values keeps the updates stable and allows the map to evolve smoothly over many measurements. On this slide, you can see 2 log odds equations. One represents the log odds value for an occupied cell, and the other represents the log odds value for a free cell. These expressions compare the probability of receiving a particular LiDAR measurement under 2 different assumptions, whether the cell is occupied or whether it is free. By taking the logarithm of this ratio, we obtain a value that can be accumulated safely over time. At every time step, the robot updates its pose and applies these log odds constants to the corresponding grid cells. This update process gradually shifts the belief toward a cell being more likely occupied or more likely free, based on all the measurements collected so far. Now let's look at how the map is actually updated. For each LiDAR measurement, we update the log odds value of the corresponding cell. If the measurement indicates an obstacle, meaning z equals 1, we increase the log odds by adding the occupied cell constant. If the measurement indicates free space, meaning z equals -1, we decrease the log odds by subtracting the free cell constant. As we repeat this process over time, each cell gradually accumulates evidence about whether it is occupied or free. In robotics, we always have to expect noise and unexpected disturbances. Because of that, we should never allow the map to become completely certain. If the log odds value becomes extremely large or extremely small, it means the algorithm believes the cell is 100% occupied or 100% free, which is unrealistic. So we introduce an upper and lower limit to prevent the values from becoming overly confident. So once we have these saturation limits, the accumulated log odds cannot grow indefinitely. Even if many measurements support the same decision, the value will eventually flatten out. This ensures that the map remains flexible and can still recover from incorrect or noisy observations. By applying these bounds, cells remain updatable even after many observations. If something in the environment changes, like people walking by or temporary obstacles, the future scans can bring the log odds back toward the correct value. This makes the occupancy grid far more robust in dynamic and noisy environments. Now, when you begin building a map, you typically start by assigning the robot's initial pose to the origin at position 0, 0. Using this initial pose, the very first laser scan is projected directly onto the map, and each beam updates the corresponding cells according to the measurement model. For example, if this figure represents the laser scan at the initial moment, the registered map on the right shows how those LiDAR hits create the very first structure of the environment. This initial scan becomes the foundation on top of which all future updates will be added. The initial map is updated directly by applying the log odds for both occupied and free cells. Once the car moves forward slightly, our next objective is to estimate how much the robot's pose has changed relative to the previous scan. To do this, we compute the transformation that best aligns the new laser scan with the map that has already been built. This process we call scan matching. Here, we will briefly revisit that concept, but now from the perspective of how it helps us build an accurate and consistent map. Here we see the laser scan collected at time t1. The red points represent the walls and obstacles detected by the LiDAR, and the blue arrow indicates the pose of the robot at that moment. This scan serves as our reference for estimating how the robot moves over time. After moving a short distance, the robot begins a left turn. At this second time instant, T2, the laser scan looks different from the robot's perspective. Even though the environment is the same, the point cloud appears rotated and shifted because the robot has changed its position and orientation. Scan matching allows us to recover the robot's motion between these two moments. By aligning the second scan with the first one, we estimate the transformation that best explains how the robot moved. This estimated pose change is then fused back into the mapping process, ensuring that the robot maintains an accurate pose while the map is updated. Remember, each laser scan is essentially a point cloud that captures the 2D structure of the environment around the robot. By comparing consecutive scans, we can track motion without relying only on wheel odometry. Now, let's look at how Hector Slam computes the transformation between two consecutive laser scans. The idea is simple. For each scan, we consider where the laser beams hit the environment, and we try to align the new scan with the map created so far. This process lets us estimate how the robot's pose has changed between two time steps. In this formulation, the pose of the robot is represented by the symbol Xi. It contains the robot's X position, Y position, and yaw angle. All scan points will later be transformed according to this pose variable. Each scan point, written as SI-XI, represents the impact point of the ith laser beam when the robot is in pose XI. The function M tells us the value of the map at that coordinate. Map cells are coded as 1 for occupied, 0 for unknown, and -1 for free. Since scan matching focuses on occupied structures, negative values can be masked to 0. If every transformed scan point falls exactly on cells whose map value is 1, the expression inside the brackets becomes 0. But in real situations, there is always noise and small errors, so our goal is to minimize this summation. The pose Xi at the current time can also be written as the previous pose plus a small change in pose. By rewriting the expression this way, the optimization problem becomes a function of this pose change. This helps us directly estimate how much the robot moved between scans. Our goal is to find a delta Z that brings this value as close to 0 as possible. To solve this optimization efficiently, Hector Slam applies a first-order Taylor expansion to the mat function m. This linearization makes the equation easier to handle while keeping enough accuracy for small pose changes. After applying the Taylor expansion, we obtain an expression that can be rearranged into the Gauss-Newton update rule. Solving this equation gives us delta C, the incremental change in pose that best reduces the alignment error. Once we compute delta Z, we update the robot's pose for the new time step. Then we transform the current laser scan using this updated pose and use it to update the occupancy grid map. Repeating this process at every time step allows the robot to build an accurate map while keeping track of its location. This video shows how the LiDAR data appears from the car's point of view. The Hector Scan Matcher takes this stream of laser measurements, compares the scans between two consecutive timestamps, and aligns them with the map being built. At every step, it updates the robot's pose based on this alignment, ensuring that both the map and the pose evolve consistently over time. This video shows the LiDAR scan data as it appears in the map frame. At each stage, the change in the pose estimate is computed to obtain the updated robot pose. Using this new pose, the incoming scans are aligned accordingly, keeping the map consistent as the robot moves. The map shown here is the result of the scan registration process we just observed in the video. Once the change in pose is estimated, each laser scan is transformed into the global frame and used to update the global map. But an occupancy grid does not immediately label a cell as a wall or free space based on a single scan. Doing so would introduce significant noise because each measurement carries uncertainty. If you look closely, the algorithm internally keeps a numerical value for every cell, not just the binary occupied or free state we see visually. This internal value reflects how many times the cell has been observed as free or occupied, combined with the confidence in the sensor measurement. Only after collecting enough consistent evidence over several scans does the system confidently decide which cells are walls and which are free. At that point, the refined occupancy grid is published as the updated map. In optimization problems like this, there is a high chance of getting stuck in a local minimum. To reduce this risk, Hector Slam does not optimize directly on a single high-resolution occupancy grid. Instead, the algorithm begins by optimizing the pose on a coarse map, which provides a rough but stable estimate. This initial estimate is then used as the starting point for optimization and a finer resolution map. For example, if the final resolution we want is 5 centimeters and we choose to use 3 multi-resolution grids, the algorithm will sequentially process maps at 20 centimeters, 10 centimeters, and finally 5 centimeters resolution. The pose found using the 20 centimeter map becomes the initial guess for the 10 centimeter map, and the output of the 10 centimeter map becomes the input to the 5 centimeter optimization. This hierarchical approach helps the system avoid local minima and improves the robustness of scan matching. Here you can see the final map that has been generated using Hector Slam. This map now becomes the foundation for all downstream tasks, such as localization and motion planning. Because of this, it is very important that we save the map once the mapping process is complete. If we can save the map, we can also load it later and use it without having to run Slam again. Let's take a moment here to look at the slide. ROS provides a package called Map Server to help us save and load occupancy grid maps. The Map Server package allows us to save the map that is currently being published on the /map topic. To save the map, we use the command ROS run map server map saver -f map name. Later, if we want to load the map again, we use ROS run map server mapname.yaml. This is the standard way to store and reuse maps in ROS. Let's pause again for a moment to let everyone read the commands on the slide. On this slide, let's come back to the idea of pose updates in Hector SLAM. At every timestamp, when a new laser scan arrives, Hector SLAM estimates the change in robot pose. This incremental pose change essentially becomes a source of odometry, so even without wheel encoders, we can still obtain a continuous estimate of how the robot is moving. Now, if we ignore the map that Hector SLAM generates, we can actually use the package purely as an odometry source. In this mode, the algorithm still performs scan matching, but the resulting pose updates are used only as odometry information, not for map building. Another option for obtaining odometry is to use the Canonical Scan Matcher package, or CSM, developed by Andrea Sensi. Both Hector SLAM and CSM provide odometry through scan matching. The main difference is this: Hector SLAM matches the current laser scan with the map that was built at the previous time step. On the other hand, CSM computes odometry by directly matching the current scan with the previous scan. Before we look at the specific TF tree for our system, let's briefly recall what a TF tree is. In ROS, TF, or transform, is the system that keeps track of how different coordinate frames relate to each other over time. Robots usually have many frames: the map frame, odometry frame, base frame, and individual sensor frames. The TF tree is simply the connected structure showing how all these frames are linked together. It allows ROS to answer questions like, where is the LiDAR relative to the map? Or where is the robot's base relative to its odometry frame right now? With that in mind, let's look at our system's TF tree. At the top, we have the map frame. Below that sits the odom frame. The transformation between these two frames is provided by Hector's odometry output. Next, we go from the odom frame down to the base frame, which represents the robot's physical center. Finally, the base frame connects down to the laser frame. This last transform, base to laser, is required by the Hector SLAM package so that it knows exactly where the LiDAR is mounted on the robot. So in summary, Hector SLAM needs base laser. It provides odom base, and the system maintains map odom. Together, these connections form a complete TF chain that enables mapping and localization. When you begin using the Hector SLAM package in ROS, you will encounter several important parameters. Let me walk you through the key ones. First, map resolution. This defines how fine your occupancy grid will be. A smaller value means higher detail, but also more computation. Next, we have two update thresholds: map update distance threshold and map update angle threshold. These control how far the robot must move, or how much it must rotate before the map is updated again. The laser max distance parameter defines the maximum valid LiDAR range. Although the default value in Hector is 30 meters, our LiDAR supports around 10 meters, so this should be adjusted. Finally, we have the log odds update factors. These two numbers determine how strongly the system should trust each scan when marking a cell as free or occupied. We discussed this earlier during the occupancy map update explanation. In the SLAM tutorial session, we'll show you how to install the package, modify these parameters, and launch Hector SLAM for your own mapping application. Now that we have completed the mapping process and obtained both the global map and a reliable source of odometry, we are ready to move on to the next major component of our navigation system. In the next section, we will introduce the concepts and implementation details of Adaptive Monte Carlo Localization, or AMCL. You will learn how AMCL uses particle filters to estimate the robot's pose on a pre-built map. and how it adapts the number of particles based on uncertainty. We will also show you how to integrate the map and the odometry that we generated today and use them together inside the AMCL localization package. This will complete the full perception pipeline, from creating the map to maintaining pose during motion to finally achieving robust localization for navigation. In the previous section, we learned how to build a map of the environment using Hector SLAM. We also saw how Hector SLAM can give us a rough estimate of the car's odometry. Now that we have the map, the next task is localization, knowing exactly where we are on that map. Knowing where we are on the map accurately is absolutely essential. Without that, we cannot decide where we need to go. Accurate localization helps us plan the best trajectory by looking ahead at upcoming corners. It also allows us to make precise control decisions about speed and racing lines. When we place our car inside the map, the first and most important question becomes, where am I on this map? Depending on where the car actually is, the decisions we make will be completely different. Even if the surroundings look similar, each corridor or intersection corresponds to a different pose on the map. So, the robot must determine its exact position and orientation, not just its rough location. Without this information, the robot cannot plan safe trajectories or avoid walls and obstacles effectively. To drive effectively, the robot must know both its position and its orientation within the map. The position tells us where we are, and the orientation tells us which direction we are facing. This is essential for actions such as adjusting steering, choosing the correct racing line, and deciding how fast we should approach a corner. In short, knowing our pose helps us decide what to do next. One simple way to estimate the car's position is to track how far it has traveled from a known starting point. This is what wheel odometry does. By measuring the rotation of the left and right wheels, we can compute the distance traveled and estimate the car's pose on the map. In this example, the green dot marks the initial position. As the car moves forward, the green curve shows the trajectory predicted by wheel odometry. We can also use the odometry output from Hector SLAM in a similar way. However, both wheel odometry and Hector's odometry suffer from inaccuracies. First, the measurement itself is imperfect, and because odometry integrates motion over time, even small errors accumulate continuously. The longer the robot drives, the larger the drift becomes. Wheel encoder odometry has an additional problem: wheel slip. High torque motors can cause the wheels to spin in place before the car actually moves. In these situations, the odometry believes the car has moved, even though the wheels are simply slipping, resulting in a completely wrong pose estimate. Similarly, odometry obtained from Hector SLAM also has limitations. Since Hector relies entirely on scan matching, it works well only when the environment provides distinct geometric features. However, in long, smooth corridors with parallel walls and very few features, the scans look almost identical from one time step to the next. As a result, the scan matching algorithm cannot detect the small changes in movement. In this video, the car is actually moving forward, and the new LiDAR hits, shown in red, clearly indicate motion. But because every scan looks nearly the same, the odometry fails to update. It only realizes that the robot has moved once a significantly different scan appears at the end of the corridor. This is a classic failure mode for feature-poor environments. So we need a solution that can compensate for all sources of odometry error, including measurement noise, wheel slippage, and failures in scan matching. These errors accumulate over time, causing the pose estimate to drift away from the true position. In addition to correcting this drift, our system must also be able to localize even when we do not know the exact initial pose of the robot. In other words, The algorithm should be capable of handling uncertainty or inaccuracy in the starting position and orientation. This means we need a method that is robust, drift-resistant, and capable of recovering or maintaining the correct pose even under difficult conditions. One solution to the localization problem is to use Monte Carlo localization, or NCL, which is based on particle filters. This approach uses many random samples to represent the possible positions of the robot. There are also other options. Kalman filters use Gaussian distributions to estimate and track the robot's position. Another method is Markov localization, which uses histograms to model the probability of being in each location. To understand Monte Carlo localization, we first need a clear intuition for how particle filters work. So let's start with a very simplified example in one dimension. Imagine a robot moving back and forth inside a long corridor. Along the corridor, there are a few doors placed at known locations. The robot has a simple sensor that can only detect whether it is next to a door or not. It also has access to odometry, which gives an approximate distance it has moved. At the beginning, the robot has no idea where it is. It could be anywhere along the corridor. So, we represent its belief as a uniform distribution. That means every location has equal probability. This is the state of maximum confusion. The graph you see is called the belief state, denoted Bell X. It describes the robot's probability of being at each position X. Now, at the first time step, the robot senses a door. This information defines a measurement model written as PZ times X. Z is the sensor reading. In this case, a door is detected. X is the possible location along the corridor. The measurement model describes the probability of receiving this door measurement at every possible location X. Since the corridor contains 3 actual doors, there are 3 positions where sensing a door is highly likely. So if we plot PZ times X, the graph will show 3 peaks. Here, each peak represents a location where a real door exists, and thus where the sensor reading, door detected, is highly probable. In other words, the measurement model has high probability at real door locations and low probability everywhere else. This is why the plot contains 3 distinct bumps, one for each door. When we combine our prior belief with the measurement model, we obtain a new belief, also called a posterior belief. This posterior belief has 3 peaks, one for each door location. The robot now believes it is most likely next to one of these 3 doors. But importantly, it still doesn't know which door it is next to. And the sensor might have been noisy, so there is still some probability between the peaks. The robot does not eliminate any possibility entirely. This distribution, with several possible high likelihood positions, is the foundation of probabilistic localization. It captures uncertainty not as a single guess, but as a distribution over many hypotheses. This idea is essential for Monte Carlo localization. Now, our belief about where the robot might be looks very similar to the measurement model above it. The robot sensed a door, so we combine our prior belief with the measurement model. This gives us a new belief distribution, the posterior belief. And this posterior belief looks like the black curve shown here. At the 3 locations where doors actually exist, the probability increases. Everywhere else, the probability decreases. In other words, the robot now believes it is most likely next to one of those 3 doors. But importantly, it still does not know exactly which door it is next to. There are 3 equally plausible hypotheses. And since the sensor could be noisy, we do not completely eliminate the positions in between. Those intermediate areas still have some residual probability. This distribution, with several possible high likelihood locations, is the essence of probabilistic localization. Instead of picking a single guess, we maintain multiple hypotheses about where the robot might be. This idea forms the foundation of Monte Carlo localization. Now let's move to the next time step, time t equals 2. According to the robot's odometry, it has moved forward by a certain distance. Even though we do not know the true position, we update our belief by shifting the entire belief distribution forward by that same amount. However, robot motion is never perfect. There is always some drift, slippage, or noise. So when we shift the belief forward, we also widen each peak a little bit to reflect this uncertainty. This is called the motion update of the belief state. It simply means our new belief is the old belief shifted in the direction of motion with added uncertainty. Here you can see the motion update more clearly. The robot moved forward, so all 3 belief peaks also move forward. Because of uncertainty in motion, each peak becomes slightly wider and flatter. We are now more uncertain than before about the exact position. This motion update gives us a prior belief for the next sensor measurement. Now, at the same time step, the robot senses again, and once again it detects a door. This means that our measurement model, P of z given x, is exactly the same as before, with 3 peaks, 1 for each door in the corridor. To update our belief, we now combine the motion updated belief and the new measurement model. This prepares us for computing the new posterior belief. Finally, when we multiply the motion updated belief with the new measurement model, we obtain the new posterior belief. Notice what happens now. Only one location, the second door, has both a high prior probability and a high measurement probability. So, the resulting belief has one dominant peak at the second door and only small bumps elsewhere. At this moment, the robot has effectively localized itself. It now knows which of the 3 identical doors it is standing next to. This illustrates the basic idea of localization using probabilistic reasoning. We maintain many hypotheses, and we gradually eliminate them until only one remains highly likely. Now that the robot has performed several motion and measurement updates, our belief distribution has become sharply concentrated near one specific location, the second door. This tall peak indicates the position where the robot is most likely located. The important thing to note here is that this belief is still represented as a continuous probability function over the entire corridor. In theory, this continuous representation is very accurate. But in practice, it is computationally expensive to store and update a full continuous function. This is why we rarely use the continuous form directly in real robot systems. To make this belief representation practical, we convert the continuous belief function into a discrete representation. This means we no longer consider every possible position along the corridor. Instead, we take a set of sample points, or particles, that approximate the shape of the belief distribution. These particles act like discrete hypotheses of where the robot might be. The sharper the continuous curve is, the more particles will cluster around that region. Instead of sampling particles at equal distances, we place more particles in areas where the belief probability is high. In this example, the belief is highest near the middle door, so particles are drawn densely in that region and only sparsely elsewhere. Each particle carries a weight, which corresponds to the probability of the belief function at that particle's position. Particles near the middle door therefore have high weights. Particles near the other doors have medium weights. Particles elsewhere have very low weights. These weighted particles together form the discrete approximation of the belief state. In the upcoming slides, we will see how these particles are sampled, how they move, and how they are re-weighted through the Monte Carlo localization process. Now, let's look at how particle filters work in 2 dimensions and how we apply them on our autonomous car. What you see here is a portion of the map that was previously generated using Hector mapping. In this map, the black pixels represent walls and obstacles, while the gray pixels represent free and traversable space. This map will serve as the reference against which we evaluate our particles during localization. The red arrow in this slide shows the robot's pose estimated purely from odometry. As we've discussed earlier, odometry alone is not reliable. It accumulates drift over time and can be inaccurate due to wheel slip or scan matching errors. So, our goal is to use particle filters to correct this odometry estimate and obtain a far more accurate pose on the map. The first step is to generate a set of hypotheses for where the robot might actually be. We do this by drawing a set of particles from a Gaussian distribution. The mean of the distribution is the odometry pose, and the covariance defines how spread out the particles are around that pose. In other words, each particle represents a possible true position of the robot, formed by adding controlled noise to the odometry. Next, for each particle, we take the current laser scan, shown here in orange, and we place it at the particle's pose. Then, we compute a correlation score between the scan and the map. Particles whose laser scan aligns well with the obstacles in the map receive a high score, while particles whose scan does not match the map receive a low score. These scores become the particle weights used for localization. Now, let's compute the correlation score for each particle. We use the formula shown on the screen. Here, A represents the map, and B represents the laser scan. The terms A bar and B bar are the average pixel values of each image, where wall pixels are assigned a value of 1 and free space pixels are assigned a value of 0. The indices M and N are simply the X and Y coordinates of the pixels. In simple words, this equation measures how well the orange scan points overlap with the black wall pixels on the map. A higher value indicates a better alignment between the scan and the map. Now, let's compute the correlation score for the first particle. Using the scan-map correlation formula, we evaluate how well this particle's pose aligns the orange scan points with the walls in our map. This gives us the score S1, which tells us how believable this particle's hypothesis is. In the next slide, we will apply the exact same process to the second particle and compare their scores. Here, we compute the correlation score for the second particle. Just like before, we align the scan according to this particle's pose and measure how well it matches the map. This produces the score S2. Now we can start comparing particles. A higher score means the particle's pose fits the environment better. Now that we have computed the correlation score for particle 1 and particle 2, we continue the same process for particle 3. Each particle proposes a different possible pose of the robot, so we overlay the scan on the map according to that pose and compute how well the walls in the scan align with the walls in the map. Here, you can now see the scores for particle 1, particle 2, and particle 3. These values, S1, S2, and S3, represent how well each particle matches the environment. Next, we evaluate particle 4 in the same way. We place the scan according to particle 4's pose, compute its correlation with the map, and add its score to the list. We now have scores for 4 particles, S1 through S4. At this stage, we begin to see which particles are more likely than others. For every particle, we place the scan according to its proposed pose and compute a correlation score that measures how well the scan matches the map. As the slides progress, particle 1, particle 2, particle 3, and the rest are evaluated one by one. Each particle receives a score, S1 through S6, and these scores represent how likely each particle is to be the robot's true pose. Some particles clearly align better with the map, while others show a weaker match. Finally, once all 6 particles have been evaluated, we select the particle with the highest weight. This particle is considered the robot's estimated pose at the current time step. Here you can clearly see the effect of using a particle filter. In the image on the left, the pose estimated from odometry has drifted away from the true position. This drift accumulates naturally over time as the robot moves. But in the image on the right, the particle filter corrects this drift by matching the laser scan to the map. As a result, the estimated pose aligns much more accurately with the environment. Now we repeat the same procedure every time we receive a new sensor update. First, we propagate each particle using the motion reported by odometry. In other words, we shift all particles forward according to how far the robot moved, and we rotate them according to the change in heading. This gives us a new set of predicted particle poses, which will be evaluated with the next scan. Next, for every particle, we perform the same scan-map correlation process we saw earlier. Each particle's laser scan is aligned with the map at that particle's pose, and the correlation score is computed. We then store these scores for the weight update. We then update the particle weights using these scores. At each time step, we first normalize the correlation scores by dividing them by the largest score among all particles. After normalization, the new weight of each particle is obtained by multiplying the normalized score with its previous weight from the last time step. This allows us to track which particles consistently perform well and to draw more particles from those high-performing regions during resampling. As we continue multiplying particle weights over many iterations, the particles with very small weights gradually shrink towards zero. Eventually, the filter ends up with only a few meaningful particles, and that makes it difficult to maintain an accurate estimate of the robot's pose. In this graph, the x-axis shows the particle index and the y-axis shows the corresponding particle weight. As the video plays, you can see that over time, only a small number of particles remain dominant while the rest collapse to almost zero weight. To prevent this from happening, we perform a resampling step whenever the number of effective particles becomes too small. During resampling, we draw new particles from the high-weight ones and then reset all particle weights to the same value. This keeps the filter healthy and prevents weight collapse. Now, let's talk about resampling in the particle filter. Consider these yellow circles as the initial particles sampled from our belief distribution. At this point, all particles have equal weight and they are spread across the state space to represent our uncertainty about the robot's pose. As time goes on, these particles will move according to odometry updates, and their weights will be adjusted using scan correlation. As the particles propagate over time, their weights begin to change. Some particles match the sensor observations well, while others do not. In this figure, the blue particles represent their updated weights. A larger blue particle indicates a higher weight and a better match with the observation. Over many updates, only a small number of particles become very large, while the rest shrink toward zero. This is a problem because the filter effectively ends up using only a few particles. When this imbalance occurs, we perform resampling. Resampling means drawing more particles near the particles with high weights and fewer particles near those with small weights. After resampling, the new yellow particles have a higher density around the high weight regions. All the new particles start with the same weight again. In this way, the particle filter starts fresh and avoids a single particle dominating the distribution. This visualization shows the XY position and orientation of each particle. Each arrow represents a particle, with its arrowhead showing direction. The size of the arrow is proportional to its weight. As the video plays, you will see only a few arrows grow much larger than the rest. When this happens, resampling occurs. After resampling, the large arrows generate many small arrows close to them, while particles far away almost disappear. This prevents any single hypothesis from dominating and maintains diversity. Please watch the video until it completes. After resampling, the particle versus weight graph resets. All particles start again with equal weight. This prevents the particle filter from collapsing into just a few dominant particles. Overall, resampling keeps the filter stable, prevents weight collapse, and ensures that the particle cloud continues to represent the robot's uncertainty effectively. This form of localization is computationally expensive because we must repeatedly calculate the correlation score for each particle. So, the more particles we use, the longer it takes to localize. To optimize this, we use a sampling method called KLD sampling. KLD sampling dynamically adjusts the number of particles based on the error between the odometry estimate and the particle filter estimate. When the robot's position is highly uncertain, the particle cloud needs to be very large, as shown in the first figure. But as the robot moves and the estimate becomes more confident, the particles converge and the cloud becomes smaller. In this way, KLD sampling removes redundant particles and significantly improves performance. Now that we understand how particle filters work for localization, let's see how they are implemented in ROS. The implementation is called Adaptive Monte Carlo Localization, commonly known as the AMCL package. The word adaptive refers to the KLD sampling method we just discussed. AMCL is used to localize a robot in a 2D space using laser scans and a pre-built map. In this system, the Hector odometry module provides the transform between the odom frame and the base frame. AMCL then provides another transform that corrects the drift from the Hector odometry so that the robot can stay accurately aligned with the map. Together, these transforms allow the robot to maintain an accurate pose on the map. Let's begin by looking at the input parameters used by the AMCL package. The very first input is the laser scan. This scan provides us with a set of distance measurements from the LiDAR sensor, and it forms the basis for matching the robot's perception with the pre-existing map. Next, we add the odometry, also known as dead reckoning. Odometry provides an estimate of how far the robot has moved over time. While this estimate may drift, it still gives us an important initial guess for localization. Finally, the AMCL package also takes in a pre-built map. This map acts as the reference that the laser scan and odometry will be compared against. With these three inputs together, the system can begin estimating the robot's pose on the map. From these inputs, AMCL produces its first important output, the corrected pose of the robot. This pose compensates for the drift that naturally occurs in odometry and aligns the robot's estimated position much more accurately with the map. In addition to the corrected pose, AMCL can also output the particle cloud. This cloud visualizes all the sample particles that the filter uses internally. It's extremely useful for debugging and for understanding how well the filter is converging. Now let's look at an example visualization in RViz. Here, the robot is moving through a hallway, and the AMCL module continuously tracks the robot's corrected pose on the map. You can also see the particle cloud updating in real time as the robot receives laser scans and odometry information. Now, let's take a look at the map being generated by the car. At first glance, it looks pretty simple, right? But this map is actually the result of many underlying processes working together. So next, let's go one level deeper and analyze how this is implemented. There are several different ways to approach the mapping problem, and many research papers compare these approaches in detail. For our discussion, we will focus on a method centered around the Hector SLAM package, which is the mapping framework used on this platform. Now we begin the section titled Particle Filters Analysis. In this part, we'll shift from using particle filters for localization to understanding why they work, how they work, and how they fit into the broader family of Bayesian estimators. At the core, our problem is to estimate the state of a dynamical system. In our case, the state of the robot as it moves through its environment. In principle, particle filters rely on the same mathematics as the recursive Bayes filter. The key challenge is this: how do we represent the belief about the robot's state? And in many systems, we also want to know how to maximize that belief. Although maximizing the belief is an important topic, We will not explore it in this lecture. Particle filters provide an efficient way to represent an arbitrary and often non-Gaussian belief distribution. In other words, when the belief does not look like a simple bell curve, closed-form analytical methods such as the Kalman filter can no longer be applied. Instead, we approximate the belief using a set of samples called particles, each representing a hypothesis of the system state. Another key idea is survival of the fittest. Particles that better explain the observations survive and multiply, while poorly performing particles disappear. This mechanism is similar to evolutionary strategies or genetic algorithms and allows us to concentrate limited computational resources on the most promising regions of the state space. Let's begin by recalling what Monte Carlo localization is based on. At its core, NCL uses a recursive Bayes filter. A Bayes filter estimates the posterior distribution of the robot's state conditioned on all sensor measurements and motion information collected over time. In mobile robot localization, the dynamical system is the robot and its environment. The state is the robot's pose, its position and orientation. And the data refers to everything the robot observes through sensors such as LiDAR or cameras, as well as odometry information describing how the robot moved. Bayes filters rely on one key assumption: the environment follows the Markov property. That means the past and future are conditionally independent as long as we know the current state. So what we want is the belief about the robot's state. That is, the probability distribution over all possible poses, given every action the robot has taken and every observation it has made. We denote observations as O and actions as A. Observations could be camera images, LiDAR ranges, or ultrasonic distances, essentially anything measured by sensors. Actions come from odometry, which converts wheel rotations into velocities or traveled distance. In summary, belief at time t is the posterior distribution of the robot's state given all past observations and actions. Using Bayes theory, the law of total probability, and two applications of the Markov assumption, we arrive at the recursive Bayes filter equation. The important thing here is that the belief at time t depends only on the belief at time t-1. At the bottom of the slide, the equation has two major parts. The integral term, this is the transition model. It expresses the probability of ending up in state xt when the robot was previously in xt-1 and executed action u at time t. The multiplication term, this is the observation model, which measures how well the current state explains the sensor observation. This recursive structure is what makes the Bayes filter feasible. One part of the derivation uses Bayes' rule, because we want a probabilistic way to express how observations update our belief about the robot's pose. When the robot receives an observation at time t, we compute how likely that observation would be if the robot were in a specific state xt. This new likelihood modifies the previous belief and produces the updated belief for time t. In simple terms, the observation model tells us how well each hypothetical pose explains what the robot sees. Finally, Bayes filters rely on the Markov assumption. It states that future observations are independent of past observations if the current state is known. This greatly simplifies the problem. We don't need to consider the full motion history, only the current state. Mathematically, this means that the probability of receiving the current observation depends only on the current state, not on earlier states or actions. Monte Carlo localization is essentially a recursive Bayes filter. It estimates the posterior distribution over robot poses conditioned on sensor data. In general, a Bayes filter solves the problem of estimating the state of a dynamical system. In our case, a mobile robot moving in its environment. The robot's state usually includes its position in the XY plane and its heading direction. Its measurements may come from range sensors like LiDAR, from cameras, or from odometry. Bayes filters rely on the Markov assumption. Past and future data are independent once we know the current state. We will make this assumption explicit in the next slides. Using Bayes' rule, the law of total probability, and the Markov assumption, we can simplify the belief update into a recursive form. This formulation lets us express the belief at time t in terms of the previous belief at time t-1, combined with motion information and sensor measurements. This recursive structure is what enables NCL to operate efficiently in real time. So now we can summarize the belief update. We estimate the current belief using three components: the previous belief, the transition or motion model, and the observation likelihood from sensor measurements. But the belief in this form is a continuous probability distribution. It cannot be computed directly in closed form. So the question is, how do we represent this distribution in practice? A very efficient approach is to approximate it using a finite set of samples. We call these particles. Here is a map of an indoor environment. If you place a robot somewhere inside this map, the very first question the robot must answer is, "Where am I?" At this moment, the robot has no idea where it is. All it has are its sensor readings, like LiDAR scans, and an existing map. Localization is the process of estimating the robot's pose on this map. Now, let's reveal one possible answer. Instead of computing a single pose directly, the robot represents its belief as a set of particles, many small hypotheses about where it might currently be. These red dots are the particles. Together, they form a probability distribution over all possible poses. Where the particles are dense, the robot believes, "This is where I'm most likely located." This is the core idea of Monte Carlo localization. Traditionally, state estimation in robotics has relied heavily on Gaussian filters. The most well-known example is the Kalman filter, which estimates a probability distribution over the robot's state. But there is an important assumption here. The distribution we are trying to model must be Gaussian, a smooth, bell-shaped curve centered around a mean. If this assumption holds, meaning the uncertainty in your state is approximately Gaussian, and your system and measurement models are not highly nonlinear, then the extended Kalman filter, or EKF, works perfectly fine. Now let's consider a situation where our belief distribution is no longer Gaussian. Real robot pose distributions can easily become multimodal or highly irregular. So the question is, how do we estimate the robot's pose when the underlying probability shape is arbitrary? This is where particle filters become extremely powerful. Unlike Gaussian filters, particle filters do not assume any specific shape. Instead, they use a non-parametric representation of the belief. The key idea is simple. We represent this arbitrary distribution using multiple random samples. Imagine that the red curve is our true probability distribution. We generate many samples scattered along the x-axis. Areas with many samples correspond to regions of higher probability. Areas with few samples mean lower probability. We can improve this idea by assigning weights to the samples. Each sample is not equally important. A larger sample, or oval, indicates a higher weight, meaning the region is more likely. Smaller ovals correspond to low probability regions. This provides a very intuitive way to approximate the entire distribution using weighted samples. On this slide, we introduce the idea of a particle set. A particle set is simply a collection of weighted samples. Each particle consists of two components, a state hypothesis and an importance weight. You can think of a state hypothesis as one possible explanation of where the robot might be. If we use 1,000 particles, we are effectively representing 1,000 possible guesses of the robot's state. Each particle also carries a weight, which indicates how likely that state hypothesis is. Taken together, these weighted particles allow us to approximate the posterior distribution. Mathematically, this posterior is expressed as a weighted sum of Dirac delta functions centered at the particle locations. The Dirac delta is 0 everywhere except at the particle's state, where it becomes infinitely high, but its total integral is 1. We can use particles to approximate arbitrary probability distributions. On the left, you see a Gaussian distribution and a set of samples underneath it. Where the distribution is high, more samples appear. Where the probability is low, samples become sparse. On the right, we see a much more complex distribution. Even here, the same idea holds. More particles concentrate under peaks, and fewer particles appear near the dips. The more particles we have, the better we can approximate the true distribution. The natural question is, how do we generate such particles in the first place? If our state estimate is Gaussian, we can sample easily using a closed-form expression. One simple technique is to take 12 random numbers between minus sigma and plus sigma, sum them up, and divide by 2. This generates numbers that approximately follow a Gaussian distribution centered at 0. This works well when the target distribution is Gaussian or has a closed-form expression. However, many distributions do not have such a simple form. So the question becomes, how can we generate samples for those more complicated distributions? One powerful technique is called the importance sampling principle. Suppose we have a target distribution shown in blue, from which we want to sample. But we cannot sample from it directly. Instead, we choose another distribution, called the proposal distribution, shown in red. We generate samples from this proposal distribution. Then, we correct for the difference between the target and the proposal by assigning each sample a weight. The importance weight is the value of the target distribution at the sample location, divided by the value of the proposal distribution at that location. This weight adjusts the samples so that the weighted samples effectively follow the target distribution. This slide shows how the importance weight behaves. If the target distribution is much higher than the proposal distribution at a certain point, the weight becomes large. If the target is lower, the weight becomes small. Through this mechanism, samples drawn from the proposal distribution are re-weighted so that the final set of weighted samples matches the target distribution. This is the core idea behind importance sampling and is essential for particle filters, which rely on weighted samples to approximate arbitrary distributions. The particle filter represents the posterior distribution using a set of samples, and it applies the importance sampling principle to update the belief over time. It acts as a recursive Bayes filter, but unlike the Kalman filter, it is a non-parametric approach. This means we do not assume a particular closed-form distribution, such as a Gaussian. Instead, we use many random samples to represent whatever distribution the robot's state may follow. The particle filter operates in 2 stages, a prediction stage and a correction stage. During the prediction step, we draw new samples from the proposal distribution, which is typically based on the robot's motion or odometry. During the correction step, we use the latest sensor observations to adjust the weights of these samples based on how well they explain the measurement. The key takeaway is that the more samples we use, the better the estimate becomes. The particle filter algorithm consists of 3 main steps. First, we sample new particles from the proposal distribution. This is the distribution we choose as system designers, and it allows us to generate samples efficiently, often using a Gaussian centered around the predicted motion. Second, we compute the importance weights. For each particle, we evaluate how well the target function, or the true posterior, matches the proposal distribution at that point. The ratio between these 2 values gives us the correction weight. This tells us how different the proposal was from the distribution we actually want to approximate. Finally, we perform resampling. This is a sampling with replacement process. we draw a new set of particles, where the probability of selecting each particle is proportional to its importance weight. Particles with high weight are more likely to survive, and low-weight particles tend to disappear, informally. You can think of this step as a survival of the fittest process. The algorithm focuses its samples on the most likely regions of the state space. Let's look at how these ideas appear in the actual particle filter algorithm. The inputs to the algorithm are our previous set of samples, representing the past belief, as well as the control inputs and the sensor observations, exactly the same inputs used in a Bayes filter. We then initialize two new sets, a predicted set and a corrected set. Both of them start out empty. Next, we iterate through all samples in the previous belief. For each sample, we generate a new sample by drawing from our proposal distribution. In localization, this usually means taking a particle, applying the motion model, and then sampling around the predicted pose. For every new sample, we compute its correction term by taking the target distribution divided by the proposal distribution. Then we add this weighted sample to the predicted set. We repeat this for all samples in the belief. Finally, we perform the resampling step. From the weighted samples in the predicted set, we repeatedly draw particles with a probability proportional to their weights. Particles with high weights are likely to be selected many times, while particles with low weights tend not to survive this step. This is often described as a survival of the fittest mechanism. The resulting set of resampled particles becomes our new belief, which we return as the output of the particle filter. Now let's look at Monte Carlo localization, which is a specific instance of a particle filter. In MCL, each particle represents one pose hypothesis of the robot. That means every particle encodes an estimated XYX, YXYX. For the proposal distribution, we typically use the robot's motion model. In other words, we ask, given the previous pose and the control input, how does the robot move? So for every particle in the previous belief, we apply the motion model and sample around it. This gives us the next generation of pose hypotheses. Then we perform the correction step. Here we evaluate the observation model, the likelihood of the current sensor data given the particle's pose, and divide it by the proposal. Since our proposal is the motion model, this simplifies the weight to the observation likelihood. So in Monte Carlo localization, the motion model drives the prediction, and the observation model provides the correction. So if we derive the particle filter specifically for localization, the overall algorithm is identical to the general particle filter. The only difference is in two lines, highlighted in red. First, during the prediction step, we draw new samples using the motion model. Second, during the correction step, we compute the importance weight using the observation model. Everything else, including the resampling step, remains exactly the same. Now let's look at how particle filtering can actually answer the fundamental question in localization. Where am I? In the very beginning, we spread particles all over the map. Each red dot is a potential hypothesis of where the robot might be. Since we don't know the robot's location yet, every hypothesis has the same weight. This forms a uniform, completely uninformative belief. As the robot starts moving and taking measurements, these particles will begin to shift, concentrate, and eventually converge toward the true pose. Here you see the robot moving through a known map. The robot starts near the top right, shown by the small green dot. The blue rays are the robot's sensor readings. In this example, sonar scans. At this stage, the particles are still spread almost everywhere across the map. The filter has not yet gathered enough evidence to confidently say where the robot is. This is the particle filter before convergence, where multiple possible locations are still plausible. Next, we run repeated cycles of prediction, correction, and resampling. Particles are moved forward according to the robot's motion. Then each particle is weighted based on how well its expected sensor measurements match the robot's real measurements. Particles that poorly match the observation receive low weight and gradually die out during resampling. Particles that agree with the observations survive and start forming clusters. After a few steps, the filter realizes that the robot must be in the long corridor, because only particles in that region produce sensor readings consistent with the map. Here's something interesting happens. The corridor is symmetric. That means the robot could be in one of two positions that produce very similar measurements. As a result, the particle filter maintains two clusters, two competing hypotheses. This is a key strength of particle filtering. It can represent multimodal beliefs, meaning it can track several possible states at once. As soon as the robot enters a room, the symmetry is broken. Only one cluster matches the new observations, so the other cluster disappears. The filter now converges to the correct, unique location. This illustrates why particle filters are so powerful compared to Gaussian-based methods like the Kalman filter, which can represent only one hypothesis at a time. Now let's talk about the resampling step. After we compute the weights for all particles, we create a new set of particles by drawing samples with replacement. The probability of selecting each particle is proportional to its weight. Why do we do this? The main reason is that we only have a finite number of particles. With such a limited number of samples, we want to focus them on the part of the state space where the probability is actually non-zero or significantly large. Sometimes, due to noise or temporary errors, a few particles drift into regions that essentially have zero probability. If we had an infinite number of particles, this wouldn't matter, because enough particles would still remain in the high likelihood region. But in reality, we can only keep a few thousand particles at best. So we need a mechanism to let the bad particles die out and replicate the good particles that match the observations well. This resampling step prevents many particles from drifting into unlikely or impossible regions. In practice, resampling is absolutely essential. Without it, the filter will eventually diverge, and you won't have any particles left in the correct region of the state space. And that completes the demonstration of particle filtering for robot localization. The robot now takes its first measurement using its two laser scanners, one facing forward and one facing backward. This gives us the initial observation needed to update particle weights. Next, we perform the first resampling step. Unlikely particles disappear, and more likely particles are duplicated. Then, we apply the motion update based on the robot's movement. The robot takes another measurement. This new observation helps refine which particles are consistent with the sensed environment. We now update the weights of all particles. Particles that match the measurement receive higher weights, while inconsistent ones receive lower weights. Another resampling step is performed. Particles with low weights disappear, and high-weight particles survive and multiply. The belief becomes increasingly focused. The robot moves again, so we apply another motion update. This step introduces uncertainty, causing the particles to spread out slightly. The robot takes yet another measurement. This measurement helps the filter correct the increased uncertainty from the motion step. Weights are updated again. Particles that closely match the measurement become darker, representing higher probability. The filter is now zeroing in on the robot's true pose. Here, we perform another resampling step. Unlikely particles die out, and the distribution becomes concentrated around the most likely robot pose. By repeating motion updates and measurement updates, the filter keeps refining the robot's position. This process gradually narrows down the robot's true location. All these steps together form the full localization pipeline using particles. This method is called Monte Carlo localization. It uses many particles to track multiple possible robot poses. Today, Monte Carlo localization is considered the gold standard for robot localization. It works reliably in complex indoor environments. Its ability to handle uncertainty and multimodal hypotheses makes it extremely powerful. And that completes the demonstration of particle filtering for robot localization. In the next few slides, we will look at how to tune a particle filter. Even though the algorithm itself is powerful, its practical performance depends heavily on the parameters you choose. So let's walk through the most important tuning options one by one. The first major parameter is the number of particles. Using more particles improves accuracy, but it also increases computation. For example, if you use 10,000 particles, you must simulate 10,000 possible poses, and each pose must process hundreds or thousands of LiDAR rays. This becomes very expensive. Fortunately, we don't need to simulate all 1,080 beams. We can downsample the scan or increase the angle step, so the algorithm only evaluates a subset of beams. The range of the LiDAR also affects the filter. Longer ranges help the algorithm find strong map correlations quickly. At the same time, you can remove useless beams, for example, beams that return nothing or beams that hit the floor. Finally, particle filters can run in parallel on a GPU. Since the weight update is similar to matrix operations, GPU acceleration significantly reduces computation. To run the particle filter or AMCL, we must provide a map through the ROS map server. This map should be a two-dimensional cost map. In the launch file, we specify the path to the map file. When RViz opens, we can set the initial pose and the filter begins estimating the robot's position as it moves. The AMCL package provides parameters for the minimum and maximum number of particles. These values control KLD sampling, which automatically adjusts the particle count based on uncertainty. If the maximum is too high, the update rate slows down. If it is too low, the localization becomes inaccurate. AMCL also defines how much the robot must move before publishing a corrected pose. There are two thresholds: the minimum translation distance and the minimum rotation. If these values are too small, the filter publishes too often with too few new observations, and accuracy becomes poor. Next, let's talk about the initial pose parameters in AMCL. These values allow us to set the robot's starting position in the map programmatically. We specify the initial x-coordinate, the initial y-coordinate, and the initial orientation angle. By default, all of these values are 0. In practice, you might manually set the initial pose in RViz by clicking the Set Initial Pose tool, but AMCL also lets you define it directly inside the launch file. This is especially useful when running automated experiments or repeatedly spawning the robot at a known starting location. Finally, AMCL also allows us to specify the initial covariance. Covariance represents how spread out the particles should be around the initial pose. A larger covariance means the particle cloud will be more dispersed, which is useful when the initial position is highly uncertain. A smaller covariance keeps the particles tightly clustered around the initial guess. These parameters help the particle filter initialize properly and avoid false convergence to the wrong part of the map. Let's summarize what particle filters are. A particle filter is a recursive Bayes filter, and more specifically, a non-parametric version. This means we do not assume a specific shape for our posterior distribution. Instead, we use a set of random samples called particles to represent it. At each step, we first draw samples from what is called a proposal distribution, which predicts how the system might move to the next state. Then, we apply a correction step to account for the fact that the proposal distribution is not exactly the true distribution we want to estimate. Finally, we perform resampling, which removes particles with low likelihood and duplicates particles in regions with high likelihood. This technique is extremely effective in low-dimensional state spaces. But as the dimensionality increases, the number of required samples grows quickly, and eventually the method becomes computationally intractable. Monte Carlo localization, or MCL, is a special application of particle filters for robot localization. In MCL, particles represent the robot's pose, including its X and Y position and its orientation theta. The motion model is typically used as the proposal distribution, meaning that particles are first moved according to the robot's predicted motion. Then, the importance weights are corrected based on how well each particle matches the sensor observations. Today, Monte Carlo localization is considered the standard method for estimating a robot's pose in a known map, and it is widely used in mobile robotics.